Thank you. Yeah, I'm still Max. I'm still from Joe University. And next I'm going to talk about joint work with my advisor, Markus, on the accuracy of password strength meters. So let me introduce Joe to you. He's a computer scientist, and he needs to create an account with the ACM. So every time Joe needs to create a new password, he has multiple ideas in his mind. And usually, in the very end, he follows his gut feeling and chooses a password he believes it's secure choice and easy to remember. But that's not always a very good idea. In guessing attacks, adversaries guess passwords in descending order of probability. Thus, very common passwords, like in this case, the password cookie, are guessed early in an attack. Therefore, Joe's account might be vulnerable to guessing attacks. One way to help users to choose a secure password are so-called password strength meters. I guess most of you have heard about them. Here's an example that shows Joe that his password is weak. Password strength meters try to nudge users toward more secure passwords by helping them to correctly estimate the strength of a given password, as users usually have a hard time to estimate the strength of a password correctly. Strength meters exist in many variations. They display their strength very differently, which makes it quite difficult to compare them. For example, they use text. As you can see here, they display weak, medium, strong. They use different colors from red to orange, green, use percentage values, scores. Sometimes I've seen meters that display the time that is required to crack the password in days, hours, minutes, seconds. There are even some meters that use entropy estimations and display the strength in bits. And in academia, we have agreed on so-called guess numbers. That's the number that is required to crack a password. Strength meters run on client or server side, and some even use hybrids. They often use simple heuristics or more advanced probabilistic models to estimate the strength of a given password. So thanks to such a password strength meter, Joe now is able to choose a more secure password. And to keep it simple, I've chosen ACM CCS 18 as Joe's password, and I photoshopped the meter to report strong. But even after ignoring the fact that ACM CCS 18 is a service-specific password, it's thus likely not very secure choice. It's hard to estimate how strong the password really is. So I Googled and I found out that some meters report that a password is weak. Others report, oh, it's a medium strong password. And some said, oh, it's a strong password, in fact. It requires 12 days to crack it. This shows that there are mismatches between different meters in the estimation. And next, I'd like to give you some more information on how previous research has measured the accuracy of password strength meters. To measure it, we first need a baseline, some sort of reference. It's important to have such a reference strength value for every password in order to be able to tell whether the meter is correctly estimating the strength or not. But even with a reference at hand, it's not clear how to compare it. In fact, by having a look at the literature-related work, we found 4 approaches that have been used in the past to benchmark different password strength meter proposals. The first one, the most obvious one, is to assess a meter's output by comparing the strength values with the reference. You can imagine this as like you compare the size of 2 boxes using a scale. If the boxes are equal in size, the meter and the reference agree on the strength of the password. If they are not equal, the scale will tell you how far the meter is off. A second approach is instead of measuring how far the meter is off, you can also differentiate on whether the meter is over or underestimating the strength of a password. This method is driven by the idea that overestimating the strength of a password is more harmful than underestimating it. I give you an example. If we overestimate, it will tell the user that the password is a secure choice, while in fact it's not, and that's super dangerous. For an underestimate, it's exactly the other way around. In this case, the meter might drive the user away from a secure password, and the user might end up choosing something else which can be less secure, for example. And then the third approach is similar to the first one, but instead of comparing strength values, we only care about the ranking. So we are not interested in how far the meter is off, but whether the order of a given set of passwords is the same when sorted by strength. As long as the meter and the reference agree that password A is more secure than password B, everything is fine. And very similar to this is the fourth approach. It's a little bit more evolved, and in this way we are using a weighted approach on this ranking-based comparison. So again, we are only interested in the ranking of a given password, but this time we consider how important a password is too. Importance is, for example, given by the frequency of a password in a distribution. So this approach is driven by the idea that meters should never make a mistake for very common passwords, but it's less harmful when the meter incorrectly judges a less common password. Next, I'd like to explain the approach that we took in our paper to find the appropriate metric to compare the reference with the meter. So our goal was to find the most appropriate metric, and this involved 3 steps. First of all, we required a reference. Then we simulated meters, and we compare various metrics that we found in the literature and that we came up with to find the metric that can be used for measuring the accuracy. As a reference, we used the LinkedIn password leak that we have heard about in the last talk. And obviously, we needed strength values, and we used the frequency, that is the count of the password in this breach. How often does this password occur in this breach? Then we split the LinkedIn leak into 2 halves by random sampling. One half is our reference, and the other simulates our password strength meter. And you can imagine that to look like this. So on the left, we have the reference and the count, and then different passwords from very common passwords and thus very weak passwords to, and it's getting stronger and stronger. And you see that the 2 distributions are a match or almost a match, and that's because of the random sampling that we used. And then next we applied some monotonic transformations, quantizations, and disturbances in order to simulate the effects that are commonly or often observed in password strength meters. So what is meant by that? I'll give you an example. So this is an example for a quantized meter output, and we quantized it into 4 bins. We have a weak, medium, good, and strong bin in this case. And if you plot this data, it will look like, as you can see on the right. In the paper, we tested various of such cases, not only quantization, and that can commonly be observed in real-world meters. Using this data, as you can see in the table, we then tested different metrics. Overall, we tested 19 metrics, and we first started with the obvious choice, correlation, but we also considered one-sided and pairwise error metrics, which account for those aforementioned over- and underestimates, mean error metrics, and various weighted variants of those. And the final recommendation is that you should use a weighted and ranked approach, or a metric that is weighted and ranked. And in our paper, and for the evaluation that you can see later, we decided on the weighted Spearman correlation, which is the Pearson correlation on the ranks. And then in our evaluation, we used 3 different data sets. If you're in this topic, and then you know them, it's RockU, a very common password breach, LinkedIn that you have seen before, and Zero Web Host, which is a web hosting company, and they were also breached and stored their passwords in plain text. So it was a good choice to use. Now, as might come up, why did we use 3 different data sets? As mentioned before, there might be service-specific passwords. For example, RockU occurs in the RockU leak more often than in the LinkedIn leak. And there are important accounts and so-called don't care accounts that are really unimportant. There are password composition policies that influence password distribution a lot. And some password strength meters that we evaluated might have been tested and trained and evaluated during development on a specific leak, especially RockU is such a candidate because it's very old. And that's why we tested multiple data sets. In our evaluation, we considered 2 use cases, the online attacker and the offline attacker. For the online attacker, we took a random sample of 1,000 passwords from the top 10,000 passwords of one of the 3 data sets that you have just seen. And as a strength estimate, we use the count value. That is the frequency, how often the password occurred in this. And for the offline use case, we took a random sample of 10,000 passwords and used the password guessability service run by CMU to get strength estimates for those as a ground truth or reference. And then we queried the meters using the Selenium framework by contacting the developers. Sometimes there was only a textual description available. There was no meter implementation, so we re-implemented them. Especially all of the academic meters, or many of the academic meters, required training and some patching to work. And how this looked like, you can see in this video. That's the Selenium framework, and we log into Facebook and try to browse to the change password page of Facebook, and then we insert our passwords. In this case, it's the online use case, so we insert very common passwords, and then we collect how strong the Facebook meter reports the password is. And as you can see in this example, Facebook uses a so-called LUTs-based strength meter, which is lower and uppercase characters, digits, and symbols. And it's simply counting how often those character classes occur. And that's why the Facebook meter judges the password 1 as a strong password, which obviously is very, very bad. In our paper, we did a large-scale comparison of 81 different meter implementations from password managers, websites, academic proposals, previous work. And if you're interested in the results, I mean, it's 2 pages. You can find it in the appendix of our paper. Coming to the results. So first of all, the academic proposals. As you can see here, the best performing academic proposals are so-called Markov models, probabilistic context-free grammars, very recently proposed recurrent neural networks, and I guess some of you are familiar with the static CVBN meter developed by Dropbox, which is based on advanced heuristics. And now we wonder what those numbers mean. It's the weighted Spearman correlation, and if the number is close to 1, it means we have high positive correlation. It's a good working meter in this case. If the correlation is 0, that means that the password strength meter is randomly guessing. And if we have a high negative correlation with -1, then you can essentially turn around the meter, and every time the meter reports a password is weak, then in fact it's strong and the other way around. So as you can see here, all of the academic proposals are close to 1, and depending on which password leak we tested, and that means the academia knows how to design password strength meters. In the real world, it's a little bit different, especially for password managers. They are sometimes do a good job. For example, KeePass has a good strength meter, and the password manager Keeper as well. You can say every password manager that relies on static CVBN, it's quite a few, do a good job. Different to that are the strength meters that can be found in operating systems. Especially named is macOS and Ubuntu Linux. You cannot trust those meters. And there are even bug reports back from 2006 that show that the meters do not perform well. And they have a very high negative correlation. So every time the Ubuntu Linux strength meter tells you that your password is weak, then you should keep it. It's a good choice. And for website meters, it's a mixed result. As expected, we have seen before, 1/3 of the meters that we tested had a very bad accuracy. 1/3 was quite okay, and 1/3 was actually good. Moreover, there is this effect of quantization that I want to talk about. So password strength meters need to translate their result into natural language, because as humans, we like that more than having strength estimates in bits or percent or something like this. And it's very crucial how those thresholds to translate into natural language are chosen. Here's an example from the password manager KeePass, and it completely fails to do this. So the KeePass meter performs quite good in the range from 0.3 to 0.8, but after quantization, the accuracy drops. And that's somewhat expected as quantization loses information. But there's also a good example, as you can see with 1Password, they did a good job in quantizing their results. So you can see that they do not lose any accuracy. If you wonder what needs to be done to set those thresholds, the answer is we don't know. It's future work. So what should be done? What have we learned? First of all, we want to, or as academics, we should work on reducing the dependency on the password distribution. That means that we build password strength meters that work with any password you give them. I mean, it's a high goal, we know, but you can see a good example with the recurrent neural network. There's the variant that is generic and the variant that is target. What is meant by that? The generic version is trained on some password distribution that we can't influence. That is the pre-trained default version. And then there's the target one, which is trained on the specific distribution. That means if we tested RockU passwords, we trained on RockU passwords before. And you can see that the correlation is higher in this case, and we should work on building meters that perform overall well. Another thing is the model size. So the Markov models and the probabilistic context-free grammars are very good, but they are server-side meters and they have database, or they require storage up to 30 gigabytes. And that's nothing that a client can afford. And here again, a good example is the recurrent neural network, as they managed to decrease the model size down to 1 to 3 megabytes. And that can be run on client side, so there's no need to transfer the passwords over TLS or whatever. And furthermore, that I have mentioned before, we should understand and mitigate the negative effects of quantization. And as academics, it's hard, but we should work on deployability as well. So ZX-CVBN success is a good example on how to do it. ZX-CVBN is available in a variety, like 15 plus different programming languages. And as developers, it's super easy to integrate. And that's a good example that we should consider. Because, for example, the recurrent neural network is currently super tough to use. They're working on improving that. And ZX-CVBN is easy to use. Furthermore, you should have this limitation in mind. We only had a look at the accuracy of password strength meter, but usability and deployability aspects are also vital for a complete assessment, and they are not presented in this work. So you might wonder, where are all of our results? You can explore them. We created a website called passwordmetercomparison.org. And there we have over 500 different measurements. And we want to maintain this. So we set up crawlers that benchmark the meters over time. And then we hope that in a few years we can report how these strength meters developed over time. And with that, I'm done. Thank you.
Very nice talk. I'm going to ask a question, and basically it's, are we studying the right problem? So we can get rid of really bad passwords by blacklisting a small list of terrible passwords. We can get rid of a lot of other attacks by doing throttling, online throttling. So we're really worried about offline attacks. So isn't the real problem we should be studying how to not have hash files leaked, rather than how to coerce users into like pushing the problem on them so that they can pick better passwords?
That's a good point. So blacklisting is a method that I would prefer instead of showing a strength meter, but they are usually combined. So we have seen a lot of strength meters that rely on a blacklist as well. And for the future, I would say that while we scanned all those different websites, we learned that, for example, Google switched off its strength meter. And Twitter did the same very recently, and we will see how it develops. Currently, there are a lot of strength meters in the wild, and I guess blacklisting will be the next hot topic. But
isn't the problem stealing password hash files?
I hope that in the future, especially with Jeremiah's work, it will become better because script and everything which is memory hard, it's super tough. Yeah. It's legacy problem, I guess. The LinkedIn problem is a legacy problem. It's from 2012, essentially. Yeah, it will fade out, I hope.
Hi, Xavier de Carnet-Carnavalet from Concordia University. I just wanted some clarification on your comparison. So when you evaluate an existing password meter, you basically compare the strength distribution with your reference, and your reference is established based on the frequencies of a part of the data sets, right?
That depends on the use case. So for getting an idea what metric can be used, in this case weighted Spearman, we use what you just said. And then for the evaluation of the real-world meters, we had these two use cases. For the online use case, we used the count, the frequency, because we only are interested in the top 1,000 passwords, and there the counts are very accurate and a good choice. And for the offline use case, we relied on the PGS, these password guessability service, which returns us or gives us a guess number based on common password cracking tools like Hashcat, John the Ripper, PCFGs, Markov models, and so on.
Okay, so for the offline case, I guess the PGS already relies on some of the techniques that have been used to actually design those academic password meters, right?
Yes.
So isn't it like comparing the same thing? You generate your
no,
guess
because
with...
I haven't mentioned that because it's related work, but the PGS service does report. It's true that it's influenced by that, but does report something called min auto, and min auto is the lowest guess number reported by any of those tools that are used by this service. Yeah, you need to check out the Usenix 15 paper from Blazor about measuring real-world password crackability or guessability.
Okay,
Yeah. Thanks. More questions?
Is there no more questions? That's